Biology's defining feature is not that it exists, but that it persists. A cell maintains ion gradients, pumps metabolites, and cycles energy endlessly. It survives by staying far from equilibrium. At equilibrium, life would simply dissolve into random chemistry. Proteins would unfold, gradients would vanish, and order would collapse. Instead, every heartbeat, every ATP hydrolysis, every firing neuron is a reminder that living systems burn free energy to hold themselves on a knife edge of dynamism. Doesn't it strike you as paradoxical that what we call stability in biology is really continuous instability, kept alive by constant flux? The scientific challenge is that physics is most comfortable at equilibrium. Thermodynamics, as first written by Clausius and Gibbs, dealt with closed systems, heat baths, engines, and phase transitions. Statistical mechanics grew up around the idea that time averages equal ensemble averages when systems are in equilibrium. But living organisms are never there. They run on constant fluxes of matter and energy. The equations of equilibrium fall silent when applied to cells, which are full of chemical cycles, driven oscillations, and molecular machines. If you want to describe a bacterium's metabolism or a neuron's signaling, you're really asking about non-equilibrium thermodynamics. Why then do we have so few tools? One reason is technical. Equilibrium systems are easy to probe because they sit still. Non-equilibrium systems fluctuate, oscillate, and often collapse under measurement. Imagine trying to weigh a running waterfall with a scale. It's always in flux. At the molecular level, most instruments were built to average over time or over populations. Spectroscopy, crystallography, bulk assays. They blur out the very fluctuations that drive non-equilibrium behavior. Another reason is conceptual. Equilibrium has universal laws. Boltzmann distributions, free energies, partition functions, but far from equilibrium, no such universal framework exists. Each system, whether it's a Belousov-Zhabotinsky reaction, a cytoskeletal network, or a catalytic nanomotor, seems to have its own peculiar rules. Scientists have fluctuation theorems, stochastic thermodynamics, and entropy production metrics, but these are only partial glimpses. There is no single agreed-upon second law for far from equilibrium life. Could it be that we are still missing the unifying principle just as Newton was missing calculus before he could write down gravity? Instrumentation is now catching up. Single molecule tracking lets us watch proteins fold and unfold in real time, rather than averaging over trillions. Optical and magnetic tweezers can pull on molecules while recording their work, and heat, high-speed microscopy, plus feedback allows freezing of diffusion to record non-equilibrium trajectories in unprecedented detail. Microfluidic chips can sustain gradients for hours, creating miniature laboratories of controlled disequilibrium. Yet even these methods only scratch the surface because biology's true non-equilibrium lies in networks of reactions across scales, from molecules to organelles to whole organisms. The haunting reality is that we still lack a thermometer for living systems far from equilibrium. We can measure concentrations, voltages, and trajectories, but we cannot yet read the global entropy production of a cell, or map how information and energy flow across its networks. Until we invent such tools, life's far from equilibrium state remains more of a metaphor than a measured law. And so the big question lingers. Will the key to understanding life lie in building better probes, nanomotors, microfluidic traps, real-time entropy counters, or in discovering the hidden principle that governs all far-some equilibrium systems? Perhaps both. The tool and the law may have to be discovered together, in the same way the telescope and planetary motion grew side by side. Biological systems cannot be understood as static collections of molecules at equilibrium. Cells continually consume energy to maintain gradients, cycles, and fluxes that oppose thermodynamic relaxation. Processes like metabolism, signaling, and movement all depend on constant dissipation of free energy. Unlike equilibrium crystals or gases, life is defined by sustained flows rather than static states. This makes biology an inherently non-equilibrium system, always in motion. Stability arises not from balance, but from perpetual imbalance. A cell maintains ion gradients across its membrane by constantly burning ATP. It is like a fountain that only exists as long as water is being pumped. Equilibrium means maximum entropy and no net flows of energy or matter. Life survives by holding itself in states that are highly improbable compared to equilibrium. Such states require constant pumping of energy to suppress entropy's natural increase. Biological order is thus a dynamic structure perched on a constant energy flow. If the input stops, the system decays rapidly. The persistence of order is bought with continuous dissipation. Without oxygen intake, humans collapse quickly as metabolic flux halts. It is like balancing a ball on a hilltop by never stopping your finger from pushing it up. In non-equilibrium chemistry, reaction rates, feedbacks, and fluctuations matter more than static concentrations. Oscillating reactions such as the Belousov-Botinsky system show how nonlinear feedback can generate waves and rhythms. Living cells are filled with networks of such oscillators and switches. Classical equilibrium thermodynamics provides no adequate description of these dynamic behaviors. Far from equilibrium, science requires new principles, often inspired by chaos theory and information dynamics. Biology thrives on these restless patterns. Circadian rhythms persist in cells even when isolated from external cues, driven by molecular feedback loops. It is like a pendulum clock that keeps swinging because energy is fed back into it. Most scientific instruments were designed to measure stable states or near equilibrium fluctuations. Calorimetry, crystallography, and spectroscopy all assume relatively static ensembles. But non-equilibrium states are transient, fluctuating, and spatially heterogeneous. Standard averages erase the very dynamics scientists wish to capture. This mismatch leaves biology's far from equilibrium core poorly probed. The instruments simplify what nature refuses to simplify. X-ray crystallography reveals protein structures, but not the non-equilibrium dynamics of enzymes under operation. It is like photographing dancers frozen in midair and calling it a description of the dance. Non-equilibrium systems amplify fluctuations rather than suppress them. This makes their dynamics noisy, sensitive, and sometimes chaotic. Traditional measurement seeks reproducibility, but far from equilibrium systems often refuse to give identical results twice. Scientists must rethink how to analyze noisy data as signal rather than error. Fluctuations are not defects, but integral to function in living systems. Capturing them requires real-time, single-particle resolution. Single ion channels in neurons open and close stochastically, yet together they produce reliable signaling. It is like a crowd shouting randomly, but producing a clear chant when heard as a whole. Equilibrium statistical mechanics has elegant formalisms linking microscopic rules to macroscopic laws. For far from equilibrium systems, no such unified theory exists. We have fluctuation theorems and thermodynamic uncertainty relations, but they apply only to narrow regimes. General principles for self-organization, adaptation, and emergent order remain elusive. Without them, biology's dynamics are only partially described. Theory lags behind nature's ingenuity. Perigogene's dissipative structures explain chemical patterns but cannot yet predict complex cellular organization. It is like having grammar rules for single words, but no syntax for sentences. Most tools measure averages over billions of molecules, masking rare events that drive function. Non-equilibrium biology demands single-molecule and high-speed methods that can track dynamics directly. Technologies like optical tweezers, AFM, and single-particle microscopy are only now approaching this level. But even they struggle with long timescales and physiological complexity. Capturing dynamics from femtoseconds to hours in living matter remains a grand challenge. Instruments are improving, but the gap is still wide. FRET can track nanometer-scale conformational changes, but often misses fleeting intermediates. It is like listening to a symphony by averaging all notes together into a single tone. The next wave of instruments must combine sensitivity, speed, and adaptability. AI-driven microscopy can recognize patterns in noise and guide measurements in real time. Quantum sensors may capture coherence and entanglement inside living cells. Microfluidics offers ways to control non-equilibrium environments with precision. Together, these technologies could transform biology into a measurable science of dynamics. New tools will redefine what counts as observable. AI-enhanced cryo-EM can now identify fleeting protein states invisible to traditional analysis. It is like giving glasses to see lightning storms in slow motion. The paradox is that life exists precisely because it resists equilibrium, yet science is best at probing equilibrium. Our instruments and theories prefer stability, while nature builds from instability. Until measurement tools evolve, the deepest principles of living matter remain out of reach. Discoveries may depend less on new equations than on new ways of looking. The future of biology lies in mastering the far-from-equilibrium frontier. A bacterium swimming up a gradient is a tiny defiance of equilibrium, forever beyond static description. It is like trying to explain a flame using only the chemistry of ashes.